Welcome to Crisis in Perception, where we examine the systems that shape our world. So today, we're jumping into Steven Pinker's amazing book, How the Mind Works, to get to the bottom of a really fascinating puzzle, the incredible hidden engineering behind our simplest thoughts. Okay, let's just kick things off with a paradox that gets right to the heart of everything. Human intelligence feels so simple, right? It's almost effortless. But the very things a toddler can do without even thinking, just seeing what's in front of them, are some of the absolute hardest problems in all of engineering. So what on earth is going on here? Well, think about it from a machine's perspective. To a robot, the world isn't made of things. It's made of data. What it sees is a massive grid of numbers, each one just representing a brightness level. Its processor then has to try and reverse engineer reality from all this flat, pixelated information. It has to guess what three-dimensional objects could have possibly created this one specific pattern of light. It's a colossal, almost impossible computational problem. And that right there gets to the core of Pinker's argument. We usually save our awe for geniuses, a Shakespeare or a Mozart. But Pinker says we should be just as amazed by a toddler simply picking up a block. And why? Because the computational problems the brain solves just to see that block, guide the hand, and put it on a shelf are in a lot of ways way more complex than the engineering that goes into rocket science. So what is the machinery behind these everyday miracles? Let's take a look inside the system. So first off, Pinker says the mind isn't just one general-purpose blob of intelligence. It's much more like a Swiss Army knife, a whole system of specialized tools, or what he calls mental organs. Just like your heart is designed to pump blood, you have mental systems specifically built for vision, for language, for social logic, and so on. This brings us to a really central idea, the computational theory of mind. This basically says that thinking is a form of computation. Our beliefs and desires aren't some kind of mysterious ghost. They're information, and they're encoded in the firing patterns of our neurons. This is how a thought, an abstract piece of information like, hey, I want to go visit grandma, can physically cause your body to get up and get on a bus. Okay, so we've got these specialized modules. But how in the world do they solve problems that logically should be impossible? Vision is the perfect example. It has to overcome what engineers call an ill-posed problem, which is basically a puzzle that doesn't have enough clues to give you one single right answer. This puzzle is called inverse optics. See, your retina captures a flat 2D image of the world. From that one flat image, your brain has to somehow figure out the 3D reality that created it. I mean, think about it. A small cube right up close and a giant cube way far away could make the exact same square image on your retina. Mathematically, there are infinite possibilities. It's technically unsolvable. And yet, your brain solves it, instantly, every time you open your eyes. So, how did we get a machine that solves impossible problems? Well, the answer lies in evolution's engineering. The architect here wasn't some grand designer, but a process, natural selection. And Pinker has this brilliant metaphor for it. Natural selection is the blind programmer. It doesn't have a plan, it doesn't have a blueprint, it just writes code through random mutation, and it keeps what works. And over millions of years, this blind trial-and-error process is the only force in nature that could produce something as incredibly complex as the human mind. So here's how that programming works, step by step. Our ancestors faced the same survival problems over and over. Find food, don't become food. Now, random genetic mutations created tiny little variations in brain wiring. So imagine two early humans. One's visual system is just slightly better at spotting the pattern of a leopard in the grass. Well, that individual is more likely to survive and pass on the genes for that slightly better wiring. Now, multiply that tiny advantage by 100,000 generations, and you get the incredibly sophisticated visual system we all have today. So, how does this evolved machinery actually work in practice? Well, it's all about reconstructing reality, building the world inside your head. And this gets to a really key shift in thinking. The mind isn't a camera just passively recording whatever is out there. No, it's a reconstruction engine. It takes the messy, incomplete 2D data from your eyes and actively builds a stable 3D model of the world, filling in the gaps as it goes. So how does it solve that impossible inverse optics problem? It cheats. The brain uses built-in shortcuts or assumptions that were reliably true for our ancestors. For example, it just assumes light comes from above, that objects are solid, and that things move in continuous paths. These leaps of faith allow it to make a very, very good guess about what's actually out there. turning an impossible problem into the simple act of seeing.
So, what feels like simple, direct seeing is really just the tip of the iceberg. Beneath the surface of our awareness, there's a universe of massive, hidden computation going on. And the everyday things our minds do are, when you really look closer, some of the great wonders of the natural world.
Now, this new perspective helps resolve a fundamental conflict, a crisis in perception about what the mind even is. For centuries, we've been kind of stuck between two extremes. On one hand, you've got the idea of the mind as this mystical, immaterial soul. On the other hand, there's the idea of the mind as a blank slate shaped entirely by culture. Pinker's framework offers this powerful third way, one that's grounded in modern biology and computer science. And you can see these three competing views laid out so clearly here. Instead of a ghost in the machine or some blank canvas, we get this third option, the mind as an evolved information processor. It's not one general learning machine. It's much more like a team of specialists where each one has been designed by evolution to solve a very specific type of problem. And this isn't just some abstract academic idea. It's a really powerful tool. For AI researchers, it suggests they should be building specialized modules, not just one giant learning algorithm. For neuroscientists, it offers a kind of roadmap for understanding the logic of the brain's wiring. And for psychology, it provides a foundational answer to the question of why our minds are structured the way they are in the first place. So I think the biggest takeaway here is this. It's a new appreciation for the profound engineering that's running just beneath the surface of your awareness. The simple act of seeing an object or understanding a sentence, it isn't simple at all. It's the extraordinary product of an incredible system shaped over millions of years. Crisis in Perception examines how systems shape belief and how better tools help us see clearly. This project is free and publicly accessible. If you'd like to support the time, tools, and research behind Crisis in Perception, you can become a supporter on Patreon. For a longer audio-based analysis of this topic, see the deep dive linked in the description. If you enjoy this kind of systems-level analysis, please like, subscribe, and comment with books or topics you'd like us to explore next.